Hello students. Today I'm going to discuss about Cauchy Euler equations from 4.7 of your textbook. This is your textbook of DE, differential equations. And I'm trying to introduce you something about Cauchy Euler equations. It would be considered at the nth order of ordinary differential equation with the coefficients. In general, they all could be function of x. They all could be variable. So to make it better to understand these Cauchy equations, we have to assume what the solution looks like. We assume that our solution actually looks like x to the m. That's our solution. So we assume y equals to x to the m as a solution for nth order linear DE of an x to the n dn of y over dxn plus an minus 1 x to the n minus 1 d n minus 1 of y over dx to the n minus 1, and so on and so forth. And finally we come with a a1x dy over dx and a naught y is equal to a function g of x. So in general we have non-homogeneous DE. But today I'm going to discuss about the homogeneous case. When we have homogeneous means we assume that g is not there, g is equal to 0, therefore this becomes homogeneous equation. In a particular case, if we assume it is a second order, so then we will have a equation like ax squared y double prime plus bxy prime plus cy equals to 0. So that would be our equation. It is a homogeneous equation, and we look for the solution. Again, the solution looks like y equals to x to the m. So I assume that looking for solution of this form, solution of the form of y is equal to x to the m. Obviously, when you take the first derivative of this, then what you have is y prime, which is equal to mx to m minus 1, and y double prime is m times m minus 1 times x to the m minus 2, and so on and so forth. But again, we did not have such equation with the variable coefficients. We had the equation like this, but with the constant coefficients. But again, the type of solution that we are looking for is this one, x to the m, so that we can take the derivative, first derivative, second derivative. It depends on your equation. If it's a third order, then you have to find y prime, y double prime, and y triple, and so on and so forth. So assume that we have this equation. If this the equation that we have is a x squared y double prime, and then we have bx y prime plus cy is equal to 0. So this is our equation. That's a DE. So that's a DE. And we look for the solution of this form. That's our solution. And that's the first derivative. That's the second derivative. So if we take this this y and y prime and y double prime, and plug in here for y and y prime and y double prime, therefore our auxiliary equation, it looks like this: am times m minus 1 x to the m plus bm x to the m plus c x to the m is equal to 0. So that becomes equal to 0. That's the equation. Then of course from here one can write actually the auxiliary equation. The auxiliary equation becomes am times m minus 1 plus bm plus c is equal to 0. So that's the auxiliary equation. Such equation, again, can be solved. It would be a quadratic equation, and if you put it in order, that becomes am squared plus b minus a to the m times m plus c is equal to 0. Now, such equation, we have three different cases. The first case is when the discriminant under the radical, if we use the quadratic formula, it is positive. Therefore, we will have two distinct real roots. The second case, when the discriminant under the radical of a quadratic formula, it is equal to 0. Therefore, we will have a repeating case. It is like we had before. So we have three cases. One is two different solutions of this, m1 and m2, and they are different. So it's called distinct real roots. Second case is when we have m1 and m2 are equal. Therefore, we have a repeating case, a multiplicity of the solution to auxiliary equation of m is equal to 2. Two equal solutions. The third case is the case when you have a complex, two complex conjugate solution. So you have two complex conjugate solution. And similar to what we discussed before, also we can discuss it here. And that is, I will put actually the result for each case. So I'm not going to go everything through the proof, but it is a lengthy proof, for especially for the third case, but I will put the result. The first case, when auxiliary equation has two different solutions and they are not the same, therefore our solution in general is a linear combination of x to the m1 and x to the m2. Actually, it would be c1 x to the m1 plus c2 x to the m2. That's the first case, and that's the solution looks like. And assume that x to the m1, x to the m2, they are linearly independent. In other words, the Wronskian of these two is not equal to 0. Second case is when you solve that quadratic equation, the quadratic equation we discussed earlier. Therefore, you will get two equal solutions when m1 is equal to m2. Therefore, what we have is similar to what we found earlier on the different methods, not this method of Cauchy Euler method. So what we have here, again, we are using the formula that we had. You have the first solution and you look for the second solution. So that's the second solution. It looks like x to the m1 ln x, and the proof is on page 167. Therefore, what we have in this case, again, as a result of the formula that we use for reduction of order formula, therefore what we found is c1 x to the m1 plus c2 x to the m2, but times ln x. Similar result we found it earlier, but that was the case when we were looking for the solution of e to the mx. But this time we are looking for the solution of x to the m. So that's the difference. Therefore, here we multiply ln x. If you have two equal solutions, if you have three equal solutions, if your problem is like m1 is equal to m2 is equal to m3, and therefore the solution that you have is x to the m1, and then you will have x to the m2, which is the second solution, would be x to the m1 ln x, multiplied by that would be ln x, and then you will have the third one, x to the m1 ln x squared. So you have 1, 2, if the third order, you stop here. And by the way, here m1 and m2 is equal, so here I should put m1 rather than m2. So this is my first solution when you have a second order equation, and this is the solution when you have a second order equation. This is when you have a third order equation, like y triple, and so on and so forth. So it remains only one last case, case 3, which is about, case 3 is about conjugate complex roots. So this is what we have. In a case of conjugate complex roots, then of course what we have, the solution looks like y is equal to c1 x to the alpha plus I beta plus c2 x to the alpha minus I beta. This is after we form our auxiliary equation, we try to solve it, and then we will see that under the radical, the discriminant under the radical becomes negative number. So if it is a negative number, like a square root of negative 16, therefore it becomes 4i plus minus 4i. Therefore, you will see your alpha, you will see your beta, alpha and beta is known, and therefore after this proof that they have it, finally one can find the solution. The last line of page 168, our solution looks like x to the alpha. I put bracket c1 cosine, the same beta, but times this time ln x instead of x. So you have ln x, and then same thing for the second term of the solution would be c2 sine of beta ln x. So this is what we have. This is the solution in the third case. I will put case solution formula number 1, solution with the formula number 2, and solution in the case of formula number 3 if you have to use it. For each one of them, I can give you one example, a numerical example. Perhaps you can we can solve it, you can see the solution, but then later on in the end, maybe I can give you one initial value problem also. You can handle that initial value problem with yourself, and if there is anything that we can discuss it for the next time. My first equation that I'm going to discuss is this equation. For instance, if the equation is this, is let's see if I find, yes, this is a good equation. So I have my equation like x squared d square y over dx square minus 2x dy over dx minus 4y is equal to 0. Solve this equation using Cauchy Euler equations. This is the Cauchy Euler equations. So we have to use y as a solution looks like x to the m. This is the form we are interested. The solution obtaining from this form. So immediately one can take the first derivative, which is mx to the m minus 1. Second derivative, which would be m times m minus 1 times x to the m minus 2. Therefore, now you have y prime, you have y double prime. We can substitute y prime, and y double prime here. So our problem actually becomes this, would be x squared y double prime minus 2x y prime minus 4y. It is equal to x squared times y double prime is this guy. So it would be times m minus 1 of x to the m minus 2 and plus or minus 2x times y prime, and y prime is this. So the times m x to the m minus 1. Then you will have what? The very last one with the negative 4 x to the m is equal to 0. This is equal to 0. Of course, they all have x to the m. You can take the x to the m from here. This would be x to the m. You see here, x and xm minus 1 would be x to the m. So these two become x to the m. This is m times m is m squared, and this is m minus 2 again. That would be m squared minus m. So when you multiply these two and this m minus 2, 2 and 2 cancel. So you will get x to the m, all of them. From here, and here. And also you have one more term, which is minus m times x to the m minus 2. So if I put all these together, what it remains for me would be this. X to the m is out. Then what I have is m times m minus 1. What I have is minus 2m. What I have is minus 4. And that is equal to x to the m for all of them as a common factor out. M squared minus 3m minus 4 is equal to 0. We say x to the m is not going to be 0. And the reason is that if this is equal to 0, the only time this is 0, m should be minus infinity. Doesn't make sense, so we are not interested for m to be minus infinity or plus infinity. Therefore, this has to be equal to 0. If m squared minus 3m minus 4 is equal to 0, and if you solve it, factoring or quadratic formula, whatever, you could find two real solutions. That means you are in the first case. Your m1 is equal to negative 1, and your m2 would be 4. So you have two solutions. So the first case says, if you look at the formula on the first case, this was our first case. First case was C1 x to the m1, C2 x to the m2. Therefore, our solution finally is equal to C1 x to the m1 is minus x minus m, and then plus C2 x to the 4. So this is our solution, the general solution of original equation that we discussed. The equation is x squared y double prime minus 2x y prime minus 4y is equal to 0. So solution to this equation is actually this. And this was a nice problem from the first case, similar to that. And I can write the solution actually, and then we can discuss it later. So I have my second problem. If I want to discuss, would be this second problem would be the case that 4x squared y double prime plus 8x y prime plus y is equal to 0. For this equation, for instance. If we have this equation and you want to solve it, again we have to look for the solution of this type. X to the m. That's important. When you take the derivative, it becomes again mx to the m minus 1. When you take one more time the derivative, becomes m times m minus 1 times x to the m minus 2. And you do take all these three and substitute here for y and y prime and y double prime. So our equation actually becomes 4x squared times y prime, y double prime, which is m minus 1 of x to the m minus 2, and then you will have plus 8x times y prime is this guy, is mx to the m minus 1, and you will have plus y, which is x to the m is equal to 0. Again, if you look at it, you multiply it, you will see that when you multiply this term by this minus 2 plus 2 cancels out. Therefore, what you have actually for this equation is and the equation by itself, 4x squared y double prime plus 8x y prime plus y is equal to x to the m is out. So you have a 4m squared plus 4m plus 1 is equal to 0. Again, this is not equal to 0, so this has to be 0. When you take 4m squared and 4m plus 1 equal to 0, and this is nothing but actually 2m plus 1 times 2m plus 1, or 2m plus 1 squared equal to 0. So you got two equal roots at this time. And the root is how much? When 2m plus 1 is 0, m is nothing but negative 1/2. So this is for the second case. We had the formula for the second case, and the formula, the second formula was here. I have it in front of my formula is here. Number 2 is y is equal to C1 of x to the solution. M1 and M2 is the same thing. So this is M1 and M2. C1 x to the minus 1/2 plus C2 of x to the negative 1/2, but times ln x. Remember this ln x when you have two solutions. And if you have three solutions equal, then that would be ln x to the second power, and so on and so forth. So this is our solution in this case. This would be our solution to the case of homogeneous, when you have a repeating solution for the eigenvalue, for the characteristic equation. I'm sorry, the characteristic. All right, so it remains only one more. It remains only one more equation. I can write it down, and that's the third case. And the third case equation becomes, again from your book, the equation that I'm interested to solve would be this guy, which is, let's say here I have it. Third case is this one. So it is x cubed, y triple, plus 5x squared, y double prime, plus 7x dy over dx, which is again y prime, and plus 8y is equal to 0. That's the third derivative. So if you assume y again to be x to the m, therefore y prime, y double prime, y triple, it is equal to mx to the m minus 1, m minus 1 times x to the m minus 2, and then this would be m times m minus 1 times m minus 2 times x to the m minus 3. So if you take all these three, y, y prime, y double prime, y triple, in the original equation, which is homogeneous, and this method that we are looking for the solution of this form, then what we are getting is actually the equation is equal to, when you substitute here, then what we have is, finally, I will write it down, it would be x to the third, m times m minus 1, m minus 2, x to the n minus 3, plus 5x squared, m minus 1, x to the m minus 2, plus 7x m x to the m minus 1, and plus 8m x to the m. You will see that they all have x to the m. Why? Because here is x to the 1, and if you take these two, this minus 1, 1 cancels, so you will get x to the m. So you have x to the m here, you have x to the m here, and you will have here also 5x squared, x squared, and this guy, if you take these two together, these 2 and minus 2 cancels, you will have x to the m. And if you take these two together, this is 3 and minus 3 cancels, so you will have x to the m. Therefore, if one can take x to the m out of all these terms, therefore what we are going to have is x to the m cubed, plus 2m squared, plus 4m, plus 8. And that has to be equal to 0. This obviously is not 0. This has to be 0. Such equation is not difficult to solve it in college algebra, because that's by factoring, by grouping. You can do it. For instance, you can take m squared out, that would be m plus 2. You can take 4 out of these two, that would be m plus 2. And then they have m plus 2 in common. You can take that one out, so it would be m plus 2 times m squared plus 4 equals to 0. That means this will give you one real solution, and this will give you two complex solutions. Solutions are plus minus 2i. This is telling you alpha is equal to 0 and beta is equal to 2. So you got a total of 3 solutions actually. For this guy, you will see, write your C1 x to the negative 2. For these, you got to use the formula number 3. We had 3 formulas, remember? So the formula number 3, we're going to use it for this guy, is this formula. Formula number 3, this one. This is formula number 3. Therefore, your final solution to this problem becomes this. Final solution becomes y is equal to C1 x to the negative 2. That's because of this is different with the other ones. And for those two, in terms of a complex, then you will have x to the alpha, and alpha is equal to 0. So when it's equal to 0, then is equal to 1. So it will be x to the 0, then I don't have to write x to the 0. That's equal to 1. So that's x to the 0, which is equal to 1. And then inside I have what? I already used C1, then I use C2 cosine of 2 ln x. 2 is beta. So it's beta ln x. And same thing for C3, sine of beta ln x. So this is a case of repeating case, which in case of repeating, you had ln x, you multiply it. But again, that's alpha and beta also. You must learn what is alpha and beta. And x to the negative 2. Therefore, the general solution, take this one out. This becomes your general solution. General solution looks like C1 x to the negative 2, C2 cosine of beta ln x, plus C3 of sine beta ln x. That's the general solution. You may write y sub g to the homogeneous equation that we have. Our original equation was third order. And that's all I had for today. But next time again, I will continue to discuss the same equations, the same topic, maybe a little more on Cauchy Euler equations. All right. Have a nice day. See you next time.